The places where there are only two applied forces on one object are the two shells on top of the book, both the little one and the big one.
Shell. The two forces on the bigger shell balance because the downward force of gravity acting on the shell is equal to the upward normal force from the book. The two forces are balanced on the small shell because the downward force of gravity acting on the shell is equal to the upward normal force from the book. The forces being applied to the big shell originate from the downward force of gravity pushing down on the shell and the normal force pushing up from the book. The same applies to the smaller shell. Gravity pulls down on the shell and normal force of the book pushes up on the shell. The forces being applied to the book originate from the weights of the big shell and small shell, gravity being applied to the book pushing down, and the upward normal force of the iPhone box pushing up on the book. The forces being applied to the iPhone box originate from the weights of the big shell, small shell, and the book pushing downwards, gravity pushing down on the book, and the upward normal force of the triangular dice, marble, and the miniature turtle. The forces being applied to the triangular dice, marble, and miniature turtle originate from the downward force of the big shell, small shell, book, and iPhone box, and gravity pushing down on either the triangular dice, marble, or turtle. The upward normal force, comes from the table pushing up on these objects. All the forces on each object are balanced because when an object is on a flat surface, the amount of downward force pushing down equals the amount of upward force pushing up.
If we remove the book from this pile, the two objects on top of the book would fall, which are the two shells. However, the objects below the book would not move, including the iPhone case, the marble, the triangular die, and the turtle. Both of these shells would fall when the book is removed because when these objects are in equilibrium, like right now, there's normal force coming upwards from the book onto both of these shells, which balances out the downward gravitational force on both of these shells. However, when this book is removed, both of the shells would fall because there is no more normal force upwards from the book balancing the downwards force from gravity. When the book is removed, these four objects would not move. The iPhone case, the turtle, the dice, and the marble. They would not move because when the book is removed, there would be less downward force onto the objects. However, the normal force would have to balance that out. For example, the iPhone, when the book is removed, there is only a gravitational force pushing downwards onto the iPhone case. However, the normal force pushing upwards onto the iPhone from the turtle, the dice, and the marble would have to also decrease to balance out the decrease in the downwards force.
A linear force and a torque are both forces. The difference is a linear force is a force applied specifically to an object's center of mass. Because it is applied to the center of mass, it causes no rotational movement and only translational movement. A torque, on the other hand, is applied off-center on an object. A torque, as a result of being applied off-center, will cause an object to rotate as well as move. The distance between where the torque is applied and the center of mass is the lever arm. The longer the lever arm, the more the rotation. So a torque is a force that causes an object to rotate, while a linear force is a force that does not, because it is applied to the object's center of mass. In our pile, many of the applied forces are torques. An example of this is the force applied by the large shell's weight on the book in the middle. The force applied from the large shell is applied off-center on the book. As a result of this, it is not applied to the book's center of mass. Without being applied to the center of mass, a force becomes a torque. So the force applied from the shell to the book is a torque, which would cause the book to rotate if it wasn't balanced out. Another torque is from the small shell. The small shell also applies a torque to the book in the same way because it's balanced off center of the book, so its downward force is a torque. The last place where there is a torque in our pile is the book itself resting on the iPhone case. The book, although it may appear to be set in the middle of the iPhone case, is in fact slightly off to the side. Because it's not in the exact middle, its downward force is not applied to the iPhone case's center of mass. Because it's a force but not applied to the center of mass, it is a torque. These are 3 examples of where the forces applied in our pile are torques. In order for a stack to remain in equilibrium, all of the forces and torques have to be balanced. All of the torques that are stacked are in fact balanced, but it may not be obvious how. For example, the torque of the book on the iPhone case is balanced. The extra weight of the book on a certain part of the iPhone case is moved from the iPhone case into the 3 objects holding it up, which are the dice, the marble, and the turtle, and from there into the ground. So, through these objects, the force of the book that would cause the iPhone case to move is in fact applied indirectly to the ground. Because the ground is a flat surface, it applies a normal force in the needed position to balance out the force applied by the book. Much like the torque applied from the book on the iPhone case, the torques applied by both shells on the book are balanced out. First of all, because the shells are both on different sides of the book, the torque of the smaller shell cancels out a portion of the torque of the larger shell. But the larger shell has a greater weight and applies a greater force, which means the force of the small shell, or the small shell's torque, is not enough to completely balance it out. The additional force of the large shell is then applied through the book onto the iPhone case and through the objects below onto the ground. Like the situation with the torque earlier, this force is balanced out by the normal force of the ground applying the needed upwards force to keep the stack in equilibrium. Because of this, our stack will remain in equilibrium even though the torques may appear to be off balance. They are in fact balanced out.
So these are the measurements we took and the calculations for the forces and the torques of each object. First, to calculate the values in the first column, we used a scale to find the mass of each object. Then, to find the amount of force due to gravity on each object, we used the equation weight equals mass times gravity to find the values we have in the second column. To find the torque, we first have to find the lever arm, which is the distance from the center of mass to the line of action of the force. To calculate the torque, you will need 2 things. First, you will need the magnitude of the force of the object that is applying the torque. And if the object is simply resting on another object, then you can just use the downwards force of gravity on that object, which is simply the weight. And you will to find the torque, you will also need the lever arm, which is the distance from the center of mass of the object to the line of action where the force is being applied. And to find the torque, you will simply multiply these 2 values. Since linear force is a force applied to an object's center of mass, to find the linear force acting on each object, you simply have to add all the forces acting on each object and then multiply that number by the downwards force of gravity, which is 9.8. For example, to calculate the linear force for the iPhone box, we would add together all the forces that are acting on it, which are from the large shell, small shell, and the book, to get the value of 0.162. Then you would multiply that value by the force of gravity, 9.8, to get the linear force of 1.5872 newtons. To calculate the linear force of the rest of the objects, we simply did the same thing,